All right. Well, good morning, folks. Welcome back. And good afternoon. Welcome back, folks. And hopefully you had a chance to take a look at some of the homework last night. I noticed that B covers material it encompasses, or it has material in it that we have not quite covered yet that involves stoichiometry. But hopefully you were able to do at least a few of the problems at the beginning where you're asked to do these types of conversions here. And so you need to be able to do these conversions based upon the balanced equation. Okay. So what we finished up with yesterday, and what you need to make sure you carry with you moving forward is that if you're given an equation like we did here, so we finished up this problem yesterday. If you're given an equation like we have here, can you take this equation and obtain information from it that would be useful for you? Let's say if you wanted to carry out this reaction, could you obtain information that would allow you to get that done? And that's what we went over in the first part of this chapter in section 1, section 12.1. What we were able to do is we were able to take an unbalanced equation like this, okay, balance it, and then obtain all this information that we had got from the balanced equation. Now understand this: none of this was given to us. Okay, none of these numbers were given to us. We were able to take the numbers that were obtained from the balanced equation and get all this information. Okay? So we were able to obtain from the balanced equation, based on what we know, we are able to obtain the number of moles of each one of the reactants. We are able to obtain the number of moles of each one of the products. Okay, so from the balanced equation, we obtain this information for ourselves. And so understand this, folks. What we did in the first section is that we were able to take a chemical equation, okay, or given a description of a chemical reaction, we were able to obtain information about that chemical reaction that would allow us then to carry out the reaction if we wanted to. Okay, so we did a problem, remember yesterday, where all I gave you was the description of the formation of water from its elements, and you were able to come up with the equation. You were able to balance it, and then you were able to tell me how many atoms were involved in the reaction. You were able to tell me how many molecules were involved in the reaction, what the masses are, what the volumes are. So all that information, all that information about quantities, that means about amounts, you were able to come up with simply from a description of the reaction itself. Okay, and those quantities are absolutely important as we move forward. Being able to get these quantities here will be absolutely important. Okay, all right. So with that said, then you were able to get moles. Okay, we did not talk about how you can obtain information about particles and atoms here. I'll leave it up to you to do that. Okay. But from this information here, being able to get the moles of reactants and moles of product, we were able to obtain information about masses. Okay? And this is where we're going to pick up for the most part today, and that is towards the end of the lecture today, is that we need to be able to obtain these masses here. Why? Because it's very useful for us to have this, absolutely useful, because we needed these values here to obtain the masses. But understand, we can't measure out moles. I mean, if I asked you to carry out this reaction, there's no instrument, there's no tool that you can use, there's no measuring device that you can use that allow you to measure out 4 moles of ammonia. We don't have that. Okay. However, if you can find the mass, which we did right here, you can measure out 68 grams. Now, it's not efficient, it's not very effective to measure out the mass of a gas, but you could. So the mass of the gas here, then, equivalent to 4 moles of the gas, is going to be 68 grams. Okay, so we can measure this out, and we have tools, we have measuring devices that can measure out masses. Okay, and so we were able to obtain this quantity here. We were able to obtain that information. Again, they don't tell us that. All I gave you yesterday, remember, was this equation. All I gave you yesterday was this equation, and you had to balance it, and then you had to figure out how many moles were associated with this reaction on reactant and product side, and then from there you had to calculate for the masses. Okay? So this information was not given to you. You had to obtain this information here. Okay? And so you were able to, so a chemical equation is rich, it's full of information. You just have to be able to interpret the equation and then be able to make sense of what it gives you. Okay? And so this is what we need to do moving forward. So if you are having issues with this here, folks, please make sure you come by and see me, because you have to be able to interpret. You have to be able to do this conversion here. This conversion here is what we learned back in chapter 10, where you had to use the molar mass, remember? You had to use the molar mass in order to find the mass equivalent to a set of moles here, okay? And so again, these numbers here, these mole values, these values here, we obtained from the balanced equation, and from a simple conversion, we were able to get the masses, okay? And so we were able to obtain the masses of the reactants, we were able to obtain the masses of the products, okay? And then we compared them, and we saw then, based on the law of conservation of mass, the masses that you start out with and the masses that you end up with should be exactly the same, okay? All right. So with that said, please make sure you review that and make sure you're able to do this, because as we move forward, okay, and then now what we're going to do is we're going to take what we learned about the information that we can obtain on our own about a chemical equation and be able to use that to answer a question like, if you start out with quantities that are not given to, that are given to you, can you find then equivalent quantities of other substances in the reaction itself? And that's what these chemical calculations are all about. And that's what we will be doing here in section 12.2. And that is, we're going to be able to calculate for amounts of reactants products given amounts of other parts, other reactants or other products that are involved in that chemical reaction itself. Okay? And so the way that I like to think about it is this. Okay? You're given a recipe for cookies, for example, that requires that you use 2 bags of chocolate chip cookies. Okay? So the recipe calls for 2 bags of chocolate chip cookies. The ingredient that you need is 2 bags of chocolate chip cookies, okay? Chocolate chips. Now, let's say you only had a bag. You only had 1 bag. You had half as much chocolate chips that you actually need from the recipe itself. Okay, what could you figure out then? How much flour you need to use at that point? How much butter can you figure out then, and be able to determine then how much less butter, how much less flour that you have to use if you only have half as much chocolate chips. And so essentially, that's what we're doing here, folks. With these chemical calculations, what we're doing then is we have a recipe. We are actually calculating for the amounts that we need. We have to come up with those numbers. But then let's say we didn't have enough, or we had too much of one of the reactants. Okay? Could we figure out how much more of the other reactant we need? And from that, could we figure out how much product we form? And so that is the essence. That is the essence of stoichiometry. Chemical calculations is basically a field of stoichiometry. And so what we're going to do then is we'll talk about these stoichiometric calculations. We'll talk about these in just a moment. We're going to go through 3 different stoichiometric calculations, but there are a number of different stoichiometric calculations that we can do. I'm just going to go over 3 of them with you, and then at the end show you how it's possible to do other types of chemical calculations as well. But these chemical calculations, these stoichiometric calculations, start with being able to recognize and use these mole ratios. Okay, so we have to talk about what these mole ratios are first. Okay, and then from there, then we can go ahead and we can start doing these calculations. Okay, so what are mole ratios? Well, we did that. We saw then with the POGL activity that we did. I introduced it to you there. We worked through a few mole ratios there, but essentially the mole ratio, folks, is the ratio of the moles involved in a chemical reaction. Okay, it's the ratio of a ratio which compares the moles of the reactants and products to each other. Okay, that is your mole ratio. So it is a ratio. Okay, so a ratio meaning then that it's a comparison. It's going to be a fraction that we're going to use that compares just 2 parts of the reaction itself. 2 parts of the reaction. It could be the reactants. You're comparing reactant to reactant. You can be comparing product to product, or you can be comparing reactant to product. But what we're doing is we're comparing the amounts in terms of moles of 2 parts of the reaction itself. And so we can obtain the mole ratio from the coefficients. Okay? The coefficients, then we will use the coefficients in order to come up with these mole ratios. Okay, so the mole ratios are simply then the ratio of 2 parts of the chemical reaction itself. Okay? All right, so that's how we're going to define this mole ratio. And since we have this, then if it is a ratio, and we can use it. Remember, a ratio basically is just a comparison between 2 separate quantities. we can use this mole ratio then as a conversion factor. And that's what we'll be able to do towards the end of the period today. And my hope is that you can do that. But what we're going to practice first is we're going to practice getting these mole ratios. We're going to practice getting these mole ratios, and then we're going to be able to use these mole ratios to carry out and do these conversions that I hope that we can get to. So we want to be able to convert between moles of reactants and products. The key is that we need to be able to convert using these mole ratios, because these mole ratios are conversion factors. They are equivalences. They are equalities that we have said are equal to one another. Okay, and so because of that, then we can use it as a conversion factor. And so what we're going to do then is I'm going to go over a few examples with you. Okay, I'm going to go over an example with you to help you see this here. Okay, so let's go ahead then and let's take a look at an example here. Okay, oops, sorry. Okay. All right, so let me go ahead and let's work through one. Let's get a balanced equation here. Let's work through a balanced equation. Let's use the one that we did earlier, where we formed water from the elements. Okay, so we have hydrogen gas, okay, reacting with oxygen gas, okay, to produce then water vapors. Okay, so that's the equation here. Balance then would be a 2 to 1 to 2. Okay, so 2, 1, 2 balances up this equation. Okay, interpreting this equation that we said then we can interpret in terms of moles. Molecules, moles, grams, and volume. Okay, what we want to do here is we want to figure out then the moles. Okay, how many moles are involved in this reaction of each one of these? Okay, so to start out then we have 2 moles. So from the balance equation, we have 2 moles of hydrogen, okay, and 1 mole, okay, 1 mole of oxygen. Okay, once we have that, then if we mix those 2 amounts together, we will make then 2 moles of water. Okay, that's what we did in the last section. Okay, which means then these are the amounts that we need. Just understand this. What this is telling us then is if we take 2 moles of hydrogen and we mix it together with 1 mole of oxygen, we put that all into one big reaction pot. Okay, and then we heat it up a little bit. We will form then 2 moles of water. Okay, what this is telling us then is that if you take 2 moles of hydrogen, in order to run this reaction all the way through, you have to make sure then you have to add in exactly 1 mole of oxygen. Okay, so in terms of the reactants, then what we're saying then is that we have 2 moles of hydrogen. We will need 1 mole of oxygen to get everything run correctly. Okay, so this is the first equivalence that we can define from this reaction. And based on this and what we've talked about back in chapter 3 and back in chapter 10, we can make this into a ratio. Okay, if these 2 are equal, we can say then that the moles of hydrogen over the moles of oxygen. Okay, this, folks, right here, I'm going to highlight for us. This is a ratio. Okay, and specifically, since this is a ratio between moles, this is what we refer to as our mole ratio. And if you notice, this mole ratio is taken directly from the balance equation itself. Okay, and since this is an equality here, and we talked about this already, since we say these 2 are equal, we can flip this around, which means then we can flip it around so that we have the moles of oxygen on top, the moles of hydrogen on the bottom, and we essentially have not changed anything, that these 2 ratios are exactly equal to one another because this starts out. So by taking this ratio, we can flip it upside down, and essentially we have done nothing to it. We have not changed it at all. Okay, and make sure you understand then that these 2 mole ratios that we've talked about here, these are equivalent. They are exactly equal to one another. Okay, which means then it doesn't matter which one we it doesn't matter which one we use. We're still multiplying by essentially 1, but which one we use will depend upon the conversion that we're doing. Okay, so this is the equivalence. We obtain this equation here, this equivalence from the balanced equation. Okay, so here what we've done in this particular mole ratio is we've compared the 2 reactants. Okay, however, we can also say this, and make sure you understand this, that the equation, this balancing reaction tells us this also. And that is, if we start out with 2 moles of hydrogen, okay, and if we had our oxygen in there, we will form exactly 2 moles of water. Okay, so this we also obtained from the balance equation. And what it tells us then is if we have our 2 moles and if we are careful, if we follow directions exactly, and we were able, if we had a measuring device that had moles, that could measure out moles, if we measured out 2 moles of hydrogen and the reaction ran well and we did everything perfectly, we should end up with exactly 2 moles of water, which means then we can set up another ratio between with hydrogen in it. But this time, though, we were comparing it to moles of water. Okay, so this is another mole ratio, folks. This is another mole ratio because it's a ratio that compares 2 different parts. This time, we're comparing hydrogen to water. Okay, so this is another mole ratio that we can make, and we can flip that around. Okay, and we will get then, and I'm sorry, okay, we can flip that around and we will get a ratio that is exactly the same, though it looks different because we flipped it around, but it is exactly the same as the mole ratio here. So therefore then we have come up with a second mole ratio. This is mole ratio number 1, okay, from the balance equation. This is a second set of mole ratios. So this is another mole ratio. We'll call this mole ratio number 2 that we, again, got directly from the balanced equation. So with that said, let me ask you this. Is there a third mole ratio that we can come up with from this balanced equation? Okay? And the answer is absolutely. Okay? So what we're going to look at with the third one then is if we, we're saying then if we have 2 moles of hydrogen, we'll need exactly 1 mole of oxygen to run this reaction. What we're saying is if we have 2 moles of hydrogen, we will form exactly 2 moles of water. So we've compared hydrogen to oxygen in this first mole ratio. We've compared hydrogen to water in this second mole ratio. What's the only comparison that we have not done yet? Well, the comparison between moles of oxygen and moles of water. And what does that mean? What does that tell us then? It tells us this, that in this third comparison, we're saying that if we start out with 1 mole of oxygen, okay, and if you measure that out correctly, you should end up with exactly 2 moles of water. So there is the third comparison that we can make between the components, the parts of this reaction. And if that's true, then we could say then that we can set the ratio of moles of oxygen over moles of water. And there it is. There is our third mole ratio. So from this balance equation, we can come up with 3 mole ratios. Okay, there's mole ratio number 3. And like I pointed out to you, just like in the previous 2 examples, we can take this mole ratio here, we can flip it around, invert it, okay, so that we have the water on top. So we have 2 moles of water on top, 1 mole of oxygen on the bottom, and these 2 ratios are exactly equal to one another. Okay? And so therefore then, from this particular reaction, we've come up with 3 different mole ratios that are unique. And then what we do is we just flip it around and come up with the other mole ratios. Okay? So those are the mole ratios. That's what we are referring to when we talk about mole ratios. Mole ratios are simply fractions. They are fractions. They are ratios that compare 2 parts of the reaction itself. Okay, they are different parts, okay, but they are 2 parts of the reaction, and we use that to compare it. Okay, all right. Let's go ahead then, and what I'd like you to do then is let's take this here, and I want you to come up with the mole ratios, okay, for this. So I give you the balanced equation. Let's come up with the mole ratios for each one of these here. Okay, I want you to take just about a couple minutes, come up with 1 mole ratio. I want you to come up with 1 mole ratio on your paper, okay, and you'll submit that. Come up with 1 mole ratio, and then I want to go over this. Take about 30 seconds, okay, to write down 1 mole ratio. Let's see if you come up with the correct mole ratio, one of the correct mole ratios. Okay, so take about 30 seconds to get that done. Okay, let's go ahead and let's take a look at this, folks. Okay, so we have our balanced equation. Okay, And so let's remember, a mole ratio will compare two parts of the reaction. In this reaction here, from the equation, we have three different parts. We have nitrogen and hydrogen as reactants. We have ammonia as our product. Okay, so you can imagine then one mole ratio then. One mole ratio then will involve, let's say, nitrogen and hydrogen. So we want to compare nitrogen, so we and hydrogen. So we're saying that one mole of nitrogen. Okay. So 1 mole of nitrogen. If we have 1 mole of nitrogen, we will need exactly 3 moles from the balanced equation here, 3 moles of hydrogen. Let's start out with this one here. Okay, so we want to start out with this equivalence. We are saying that those two amounts, I'm sorry, I left that out. We left out an important part here. Okay, nitrogen here. Okay, we're saying that those two are exactly equal. If that is the case, then, okay, the mole ratio we can form from this, then the fraction would be then 1 mole of nitrogen over 3 moles of hydrogen. And we can invert that, we can flip that around, and we will get then 3 moles of hydrogen over 1 mole of nitrogen. Okay, and so even though they don't look quite the same, I mean, one is the reciprocal of the other ones, these two are equivalent. That means they represent the exact same number, the number 1. They both are equal to 1, but we have the 2 mole ratios there. Okay, so that's mole ratio number 1. Let's go ahead and take, and I'm running out of time here. Let me do the remaining 2. All right, so we have, for the first mole ratio, we compared nitrogen and hydrogen. We have these two as part of a mole ratio. What about nitrogen? We take nitrogen and ammonia and compare those two. So that means then we have 1 mole of nitrogen. And if we have that, that is equivalent to 2 moles of ammonia. Okay, so using this equality right here, let's write down the 2 mole ratios associated with this equivalence. So it'd be then 1 mole of nitrogen over 2 moles of ammonia. Okay, so that's 1 mole ratio, and we can flip that around. Okay, take the reciprocal of that. So we have then 2 moles of NH3 on the top and 1 mole of N2 on the bottom. So that is a second set of mole ratios we can obtain from the balanced equation. Again, these two, even though they're reciprocals, they represent essentially the same conversion factor. Okay. All right, let's take a look at the last one. Let's take a look at the last one. Okay, and let's write that out. So let's see what we've done so far. We've compared nitrogen. We have these two in 1 mole ratio. We have nitrogen and ammonia in our mole ratio. So we've defined 2 different mole ratios based upon those 2 comparisons. What's the last one? What's the only comparison we have not done yet? Well, the one between hydrogen and ammonia itself. Okay, so we have an ammonia. So we have then 3 moles of hydrogen. Okay, that's going to be equivalent to and equal to 2 moles of ammonia. Okay, so this represents then a third equivalence. That means those 2 values are exactly equal, which we can use then to set up a third set of mole ratios with. And so let's go and write that out. So we have then 3 moles of hydrogen over 2 moles of ammonia. Okay, and taking the reciprocal of that, we get another mole ratio. But again, this mole ratio here and the one we just formed here are exactly the same. And that's why we say they're equal moles of hydrogen. Okay, so those are the mole ratios that you can come up with from this balanced equation. 6 of them, 3 that are unique, but 6 of them in total. Okay, all right, very good. So what I'd like you to do, just to finish out here, what I'd like you to do, and I'm going to clear this out here really quickly, and I know I'm running a little bit over time. I want you to finish up here with number 8 in your problem set. We'll start with this on Monday, okay? I want you to write out all the possible mole ratios that you can obtain from this equation. Make sure you balance it first, folks. You got to make sure you balance it, but I'd like you to finish up the period by taking number 8 here in your problem set. I want you to write out all the mole ratios that can be derived from this equation. And we'll start with this particular problem on Monday. Okay, but make sure you get that done. Make sure you try set B from chapter 12 here. I'll extend the due date till Monday. I'm sorry, Tuesday night. I'll push it through till Tuesday night because I want to talk about the um, uh, conversions that we will need to do. But I'll go ahead and get that done. But you please make sure before you finish the period for the day, go ahead and write out the mole ratios for this particular equation, and then make sure you turn in all your work, submit it, and then we will hold on to it. Don't toss it. Okay, and hold on to it, and then we will go over this problem on Monday, and then at that point you compare your answer to what we come up with on Monday. Okay. All right, folks. Well, have a good weekend. Finish up this problem, and then have a good weekend. And I will see you on Monday.